Can everyone hear me okay? Microphone working? Yeah? Cool. Okay, afternoon everyone. I'm Andy Davis. I head up NCC Group's Transport Cybersecurity practice. Shortly in the talk I'll be joined by Dave Clare, who's our Automotive Tech Lead. And the two kind of main thrusts of this presentation. The first one is a bunch of tools and techniques and methodologies that we've developed over the years. We've been testing vehicles, and also a number of different kind of anecdotes, war stories about things that we've seen as a result of testing using these tools and techniques. So a little bit of an agenda. We'll start off with the obligatory attack surface slide that if you've been to any automotive cybersecurity talks, you'll have seen lots of examples of these, but it's really to give you an idea of just how complex and large the attack surface is in the connected car space. We'll then go through all the different security assessment techniques that are kind of within our arsenal. Then talk about some of the common themes that we see throughout the automotive space, so different elements within that attack surface. And then we'll talk about secure development lifecycle, so how the industry can address these problems, and finish off with some Q&A. So the attack surface slide, probably bigger than a lot of people's attack surface slides. Normally you just get a picture of a car and pointers saying USB and Bluetooth, that kind of thing. But I wanted to really give a big picture of how connected the connected car infrastructure is these days. And it's not just the wired and wireless interfaces on the vehicle itself, it's all the onward connectivity as a result of telematics. And telematics is a real growing industry at the moment. So all via the mobile network at the moment, and via internet data or specific telematics data to telematics service providers. And just to show all these different providers of data and consumers of data around telematics. So, all the way from, the insurance industry looking at how well you're driving your car so they can work out whether to reduce your policy or the cost of your policy. Through to things like connections through to emergency services, so that if your car breaks down or is in an accident, the car can tell the emergency services where you are and whether the airbag's been deployed, that kind of thing. The majority of the stuff that we're going to talk about in this presentation is around the vehicle itself and the assessment techniques we have against these different wired and wireless interfaces. So we're not going to concentrate too much on the telematics stuff. So, RF interfaces, communications via wired interfaces such as USB, that kind of thing, diagnostics. In fact, the first chunk of the talk is going to be about diagnostic stuff. So we'll kick off with attacks that require you to physically connect to wired interfaces on the car, and we'll talk about some diagnostic stuff. So if I can bring Dave up here and hand this over to him, he can. There you go, clip that on somewhere.
Come on.
Seamless transition.
Yeah, great. Is that working? Right.
Yeah.
Okay. So this section of the talk is going to be about unified diagnostic services, which is a diagnostic protocol that all cars use and that the mechanics use to interface with the vehicle when you take your car in for repair. This is the protocol that they're going to use to diagnose faults on the vehicle. However, we've found through testing that you can impair safety critical functions of the vehicle, things like disabling the steering, killing the engine, security issues like adding and removing keys from the immobilizer, that kind of thing. You also have the problem of manufacturer IP theft, which is because you can download the firmware of the ECU. This is how people modify cars, so modify the air fuel maps to increase horsepower, that kind of thing. And we also do a lot of CAN gateway assessments, which are kind of, a lot of manufacturers are starting to implement gateways in the car to prevent messages transitioning from one bus to another. But the problem with that is that the gateway itself then becomes the point for attack. So I created a tool called vmap, which is basically, I call it vmap because it's kind of like nmap for vehicles. It's a Python tool which enumerates the services that are supported on all the ECUs in the vehicle. It uses the Linux socket CAN library, so any compatible hardware interface will work. So you can have CAN, CANFD. But UDS, the protocol, is actually an application layer protocol, so it's data link agnostic, so you can swap it out for over IP if you wish. So at the moment, it can do various things like detecting the ECUs that are in the vehicle, the supported diagnostic functions of the ECU. You can authenticate to the ECUs, which enables you to read and write data in volatile and non-volatile memory. So UDS is basically a data link independent a diagnostic service for road vehicles. As just an example of a few of the services there from the ISO standard. Not all services have to be supported. Not all services are interesting from a safety or a security perspective. And some of them require authentication, which we'll move on to later, before you can use them. So ECUs in a vehicle have a physical address in the range 700 to 7FF hex if it's 11-bit, or a lot larger range if it's 29-bit. And you can detect these ECUs by sending a UDS request, a service request, to all the values in the range and listening for a response. If you get a response, you know that there's a live ECU there. So the services we use for that are diagnostic session control and tester present, because they're kind of benign services which just tell the ECU that you want to do some diagnostics. And the ECUs have to respond with a positive or negative response for these services. So just a quick demo of that. No. So what we're doing here is we're just sending a diagnostic session control request to all ECUs in the range 700 to 7FF and listening back for a positive or negative response. We don't care at this stage if it's positive or negative, since we just are after the address of the ECU. So they're the arbitration IDs. You can see there that we have ones 730, 731, down to 7E0 there. And at the end, you can see it gives you a list of the different ones that are available.
What were you connected to there?
That was just through the OBD port. No, sorry. How do you exit your thing? I think your mouse. There you go. Right.
Better if there's a mic connected.
I think the mouse is broken on this. No, I can't go back in. There you go. Right, sorry about that. Right, so UDS Service Enumeration, the services that we've showed a previous slide of, they can be enumerated in pretty much the same way. You're just listening for a positive or negative response. You're kind of brute forcing the services. So the ones in green there, they're in the standard as defined values that are known. So this is an example of diagnostic session control. So you have mode 2, mode 3, and mode 4 there, and they are what they are: programming session, extended session, and safety system diagnostics. The ones in red underneath are split into 4 categories. The sub-function, so in UDS you have a service and then you have a sub-function. The sub-functions are defined in byte ranges. So the first lot of byte ranges is vehicle manufacturer specific. So they're sub-functions that the manufacturer can assign to do certain things. So the people like Ford, GM. The second range is a system supplier specific, used by the tier 1 and tier 2 providers. So that'll be like Bosch, Continental, the people who actually make the ECU. And then the other ranges are either reserved for future use or are undefined. And those are the ones that are interesting because, as we've seen, people seem to be sticking loads of different random things in there that cause all kinds of havoc on the car. So how you actually detect if a service is active is you're just listening for a positive or negative response. So on the left there, you have a positive response where you 7E0, we're telling the ECU, we're requesting service 10, mode 3. Now, if it's a positive response, it responds back by the second byte is just added 40 hex, so that becomes 50, and then the sub-function is after that. So you can tell that's a positive response. On the right, you have a negative response, which is it replaces the service with 7F if it's invalid, and then the the 22 there is conditions not correct. So that's like the error code for why it didn't work. So conditions not correct can be things like the car is in motion and you've told it to do something which is unsafe. So all you need to do is loop through the byte ranges that are defined in the standard until you get a positive response. And it's interesting when you do this while the car's running or while you're driving, so you can find all kinds of different services which either intended to perform a certain function or they just by accident happen to break something, which is something we'll demo now. So this is a demo of attacking the powertrain control module using one of the discovered services. Oh, you bastard.
Right, we're in a different one of our research vehicles, and the engine is currently running, and it's about to demonstrate that by sending some specific data onto the canvas, we can actually kill the engine while the vehicle is potentially in motion. This vehicle is currently static, but we'll demonstrate that the engine can be killed by an attacker with unauthorized access to the canvas. And the engine has now stopped.
And this is a second video attacking a different module. This is the PSCM, the power steering control module.
Okay, so we're currently inside one of our research vehicles, and we're going to demonstrate one of the dangers of an attacker gaining unauthorized access to the canvas. So they demonstrate that the steering is currently working fine, the engine is running in the vehicle, and now if we send certain specific packets onto the canvas, we can see that the steering is completely locked, which would be very dangerous in a real driving scenario. And then when we stop sending the packets, the steering is working fine here. And it's worth mentioning that this is not a specific vulnerability with this vehicle. It's something that is a widespread issue if you manage to gain unauthorized access to the canvas.
And why? Right. So that last one there with the power steering control module, that was pretty interesting because normally if you were to impair the ECU in some way, you would still be able to turn the vehicle. It would just feel like your power steering belt had snapped and it would just be kind of difficult to turn. But on that one, the motors actually failed closed, so you actually physically couldn't move the wheel because the motors were locked, so that's kind of unusual. And these two issues, killing the engine and impairing the steering, is an issue that we found on pretty much every vehicle. In some way, there will be a way to do that by abusing the diagnostic services. So there's yeah, so we didn't video that, but yes, you can do that. Yes. So yes, it is. Yeah. So security access. So some of the services require a sort of authentication mechanism, and this works by having a symmetric key embedded in each ECU and a corresponding key embedded in the OEM diagnostic software that the manufacturers use to diagnose faults. It's a challenge response thing, so when the diagnostic tool gets plugged in, it asks the ECU for a seed value, and the ECU sends the seed back to the diagnostic software, and the diagnostic software will have a copy of the algorithm for that manufacturer, and it will put the seed together with a key, this symmetric key, which is also for the ECU, together into the algorithm, and out comes the response. That response is sent back to the ECU, and it's then unlocked, which means you can use some of the protected services. Before you give an example of that, there's other issues we found with seeds, the seed value itself. So we found issues where the entropy is poor, and issues where things like the seed is the same every single time for every ECU. Sometimes it's the same always, sometimes it's the same for the time you have the ignition on, and then you power cycle the car and you'll get a different one. I've seen it where the seeds vary between 2 bytes only, which is easy to brute force, or all the way up to 32 bytes. So it kind of varies between manufacturer and the use case. But in most cases, it's way easier to just reverse engineer the diagnostic software with IDA Pro or something like that to get the algorithms out. So what's going on here is we have a list of seeds, a list of keys, sorry, and you can see there we're asking for a seed and trying. Oh, sorry. Sorry. Right. What's going on there is we were brute forcing the key for each ECU. So we pulled the seeds out of a DLL file, the keys out of the DLL file in the OEM diagnostic software. But if you don't know which key is for which ECU, but you do have the algorithm because you reverse engineered that as well, you can try each key in rapid succession until it authenticates. On most cars that won't work because you will get locked out after 3 invalid attempts, and the lockout is exponential. So you have to take the ECU out of the vehicle, put it on a bench, and then find some kind of way of resetting the CPU to try and bypass the timer, which if the value is held in RAM, which is a bug in itself, you can bypass the timing restriction. If it's in NV RAM and it's exponential, then you kind of you can't go any further. But if you don't know which key is for which ECU, you just need to hook into the diagnostic software whilst you're performing a function. So there might be a button in the software for adding a key to the immobilizer. So if you want to find the key for that, the password for that ECU, you would just hook into the software and do that function, pull out the right key. So there's no kind of guide to which services are protected. It's down to the manufacturer and the use case. The ones that typically are protected are ones that you can use to read and write memory and change the ECU in some way or use some kind of proprietary diagnostic function. So these include things like anything where you can read and write by address, anything where you can read and write by identifier. So a data identifier in UDS, it's just a 2-byte hex value which corresponds to a piece of memory, a location in memory which holds some data in the ECU. So for example, F190 is always the VIN number for the car in the ECUs. Oops, sorry. So here, what we're going to do is a demo with authenticating with the ECU and changing the VIN number for the vehicle. So you can see there that the VIN, that's the proper VIN for the vehicle. And then we authenticate with a known secret and write our own value into memory and then read it back. And you can see there I've changed the VIN number to a cross-site scripting value, which is interesting because a lot of the diagnostic software that manufacturers use is HTML based. So there's potential for attack vectors there. And also, as Andy said in the beginning, the telematics, most of the systems always read the VIN number of the vehicle and it gets put back into a report. So someone will log into the thing, you could get caught by a cross-site scripting bug. It's a pretty interesting attack vector. Right, so this is a bonus video, bonus slide. Something we've been playing around recently is ISO 26021, which is the end-of-life activation of onboard pyrotechnic devices for vehicles. So that sounds cool, but all it is when a car gets pulled in for scrap, the airbag systems and seatbelt restraint systems contain a substance called sodium azide, A-Z-I-D-E, I don't know if I said that right, and that's dangerous. And when cars go into those big industrial shredders, you can't shred the vehicles with these things in it because it's toxic and they're explosive. So you have to have something called a pyrotechnic deployment tool, which you plug into the vehicle and it detonates all the devices and then you can shred it. So this is a standard. And deployment over CAN is supported, so you could technically do this, but most of the vehicles that I've interrogated with vmap report back that an ACL is required. An ACL in this case is called an alternative communications line, meaning that you would have to plug into the OBD or have access to CAN either remotely or locally, and also plug physically into the restraint control module. So unfortunately that's not an attack vector for that particular vehicle. However, if you can authenticate and then use a particular data identifier, specific DIDs in this case in that screenshot correspond to the configuration of the restraint control module and the supplementary restraint system. So you can see there I've written some data in and reran vmap, and it's reported back that the airbags have been deactivated on all of the ones that are in the car, which is kind of just as bad as them going off, but slightly less spectacular. So that concludes the diagnostic portion of the talk. So it's worth pointing out that even though this is all physical access stuff where I've been testing here, this is used as a post-exploitation tool to find out the kind of nasty things you can do on CAN once you've got remote access and arbitrary CAN access. So if you have access to CAN, you can do any of the things that have been demoed here. Where did I put that? There you go.
Cool, thanks Dave. Okay, so we're now going to go on and talk about some of the other tools and techniques that we use for other interfaces other than the onboard diagnostic stuff. So first of all, USB. I've done quite a lot of USB research over the years, developing a number of different tools and techniques. The picture there shows a face dancer board, which some of you may have used at some point or another on pen tests. It's open source hardware that allows you to basically emulate USB devices. And I wrote a tool called UMAP, which is open source, that allows you to not only go through and enumerate what devices are supported by the host, to emulate those different devices, and then based on the different USB specifications for those different device classes, fuzz them and identify vulnerabilities in the host. But in addition to that, some of the other stuff that we've done around USB within vehicles is pretty interesting. I mean, we've found lots and lots of vulnerabilities in device drivers, but also one interesting example that we saw. We were doing a combination kind of active runtime testing using tools, and also a hardware teardown that resulted in us being able to pull the firmware off the head unit, the infotainment system in the car. And someone was looking through the firmware, kind of strings of the firmware, and reverse engineering using IDA Pro, and found something that looked pretty interesting, and came up to the group of guys that were doing the testing in the vehicle and said, we've got something that we want you to try. We're not quite sure whether it works, but we think that we've got an attack here. And it turned out that the authentication mechanism that was being used to determine whether firmware that was going to flash the head unit on a USB stick, the way the authentication was done was it was looking for the presence of a file with a certain file name to also be on that USB stick. So that file didn't have to have any content at all, it just had to have a certain file name. So if a file with that file name was present and a binary blob file was also present, it would flash the firmware of the head unit. Great authentication. So stuff like that with USB is always quite interesting. Video protocols is another interesting area. I mean, as we're seeing more and more cameras and sensors in vehicles for devices and mechanisms to help parking more easy for the occupants. Lots and lots of cameras and different video protocols, and a lot of people aren't aware of the fact that there's lots of bidirectional communication that goes on in these video protocols, especially the likes of HDMI. And we've got dedicated test tools that allow us to emulate those different protocols and fuzz the video drivers, basically. Again, those tools are open source. They're available on our GitHub repo. We see lots of examples of media protocols that are supported in head units. So by head unit, I'm talking these infotainment systems. They used to be called car radios, and they got bigger and bigger screens. Typically called head units in the automotive industry. But they're supporting more and more of these media codecs, so videos, different audio formats and image formats. Why anyone would want to put their photo library in their car, I'm not quite sure, but the capability is there to fill the hard disk with photos so that you can look at them all on your head unit. But as we all know, the parsers for these complex media codecs are often buggy. and can result in things like memory corruption vulnerabilities. And important to note, and this will kind of link into something I'll talk about a bit later, that the parsers that are used for these different codecs, you'll often have like one central parser that parses data regardless of what source it comes from. So, when we're testing within the vehicle, it's quite easy to use USB as a way of injecting these different images in a kind of fuzzing context. But if you've got some kind of wireless protocol that allows you to send an image or some other kind of media to the vehicle, it will be that same parser that's processing that data. Now, I've got implications of using open source media parsers there, because often when we find vulnerabilities as a result of fuzzing with embedded systems, it's quite difficult, if it's an in-vehicle assessment, to actually triage those bugs and gain a real kind of understanding of the root cause and how exploitable they are, that kind of thing. So if you can determine that the parser or any other component within the vehicle that you're fuzzing is actually an open source component, you can then do your fuzzing kind of off-board, and it's much easier to triage. So, we've had examples in the past, again, where we've been doing a combination of hardware teardown, firmware extraction, reverse engineering of that, alongside fuzzing within a vehicle. And the people doing the firmware analysis have seen indicators like strings with version numbers or application names, library names, that show that it's an open source component. So that then makes our job much easier, because if we're fuzzing it and we find a crash, we can download the open source implementation of that library and see if it also crashes it when it's running on Linux, and then it's far more easy to work out what the real world impact of that is. So, I've talked about fuzzing. We've got lots and lots of different fuzzing tools. We've got a custom fuzzing framework called Fuzz Labs that allows us to kind of interface with lots of different wired and wireless protocols to test all this stuff. So onto the wireless side of things. You see Bluetooth in most cars these days, primarily used for pairing your mobile phone, allowing you to upload your address book to the head unit. And we do a lot of testing around Bluetooth, both with the device paired and unpaired. So, when you pair your device, you have to go through this mutual authentication process with pins. But of course, as part of that process, there is this kind of sub-protocol that is working to perform that pin authentication. And if you find a vulnerability in that, you can attack Bluetooth without knowing the pin and without having to pair. So we've demonstrated kind of pre-pairing and post-pairing attacks against Bluetooth with one of our tools. This tool isn't currently open source. Infrared, this is an interesting one. So we were doing a whole vehicle test for a client, and it had rear seat entertainment. So you had LCD screens in the seat backs, so the rear occupants could watch DVDs and the like. And they had an infrared remote control handset, so that from the back they could control the head unit. And we thought, okay, well, this looks interesting to have a little play with. And the thing that made it more interesting was when we realised that infrared actually works through the car windows when the doors are closed and the car is locked. And the first thing that we did was we wanted to be able to fuzz the infrared parser to see if we could identify, if we could put it into some kind of diagnostic mode or demo mode to identify functionality that wasn't supposed to be there. And because of the limitations of these consumer infrared protocols, you're unlikely to find things like buffer overflows, memory corruption, vulnerabilities. But we did identify some scenarios whereby it was clearly changing the the refresh rate, for example, on the screen, so the screen would go black, but nothing particularly exciting. And anyway, we kind of moved on to other things in the assessment, and later on we'd identified some exposed CAN bus wiring on the vehicle. So the stuff that Dave was talking about, you need to plug into the onboard diagnostics port, which is normally underneath the dashboard. But if you can find exposed CAN wiring outside the vehicle, then, and you can plug it into there, then obviously that's an interesting attack. So we had found this at a certain point on the outside of the vehicle, but when the car was locked and alarmed, the CAN bus was asleep. So even though we could connect into it, we couldn't actually perform any of the techniques that Dave was talking about. We needed to wake the CAN bus up. And then we remembered this infrared tool that we developed and the fact that it worked through car windows. So what we were able to do is actually, when the car was locked and alarmed, send infrared through the car window to the head unit, which would actually turn the head unit on, which changed the overall power level of the vehicle and woke up the CAN bus. So once the CAN bus was then awake, we could then do the attack via the exposed CAN wiring. Tyre pressure monitoring systems. So in some countries around the world, like in the US, this is mandatory that you have some form of tyre pressure monitoring so that the driver can tell if the tyres have burst or you've got some kind of puncture for safety reasons. And obviously with the wheels rotating, the easiest way to do this is actually to put RF transmitters on the tyre pressure valves on each of the tyres, and they look a bit like that. So they've got built-in radio transmitters within them, and they then transmit periodically the current tyre pressure to a receiver that's within the vehicle, and it will then display on the dashboard what your tyre pressure is for each of those tyres. One of the tests that we did for a vehicle, the types of vehicles they had, they were very concerned about what they called the VIP hijack scenario, where if as an attacker group you could follow a VIP's car and make the chauffeur of that VIP's car think that all the tyres had burst. Because if they think the tyres have burst, it's kind of like a social engineering attack, really. You can convince them to pull over, and then you could physically hijack the vehicle. And using software-defined radios, we demonstrated that it's pretty easy to do replay attacks against these type of protocols. Reverse engineering the RF protocol that's sent from the tyre pressure sensor to the onboard receiver was reasonably trivial. And it was easy to demonstrate that using a following vehicle and a directional antenna, this was an easy attack to pull off. And that's pretty much across the board with these TPMS sensors. We haven't found examples of these radio-based TPMS sensors that you can't do replay attacks against, because they just hadn't considered the requirement for security within them. There is another type of TPMS called indirect TPMS that, instead of using RF transmitters on each tyre, it actually measures the wheel rotation using the ABS ECUs, but they're not quite so popular. Certainly not within 4x4 vehicles, actually, for a number of different reasons. Wi-Fi. So we see lots of examples of Wi-Fi clients and Wi-Fi hotspots within vehicles, and a range of different potential attacks scenarios against each of those. One interesting one that we came across was, although in the vehicle that we were looking at, it didn't have a default hotspot enabled, it had a Wi-Fi client that would always try and connect to previously associated hotspots that the owner had configured it to. So you could think of a scenario whereby the owner of the vehicle will configure it to their home Wi-Fi, so when they drive home and sit on the drive, they could sync their music, their MP3s with their car and their NAS at home, for example. And as an attacker, you could find out what the SSID was of the home network that they were connecting their car to, and you could set up a rogue access point, and their car would then connect to you. But the interesting point here was when you connected to the head unit, there were a bunch of exposed services, one of which was SSH, and there was a default root password on SSH, which you could connect to via the Wi-Fi. So once you'd connected to that, because of the lack of segregation between the head unit and the vehicle network, so the CAN bus that Dave was talking about, although you couldn't send arbitrary CAN data, there was an API that you could communicate with, and we were able to turn off the safety functions within the car via this wireless attack. So ADAS features, the safety functions that you see on cars, one of the ones on this vehicle was advanced emergency braking. So if the vehicle owner had enabled that, we were able to disable that via Wi-Fi without them realizing, which is quite serious. Remote keyless entry, more and more we're seeing vehicles with this as an option. So essentially the way that it works is instead of the vehicle owner having to press a button on their key fob, as long as they've got their key fob in their pocket, the moment they touch the handle, the door handle, the car sends a signal via 125 kilohertz to the key fob to find out if it's in range. If it's within around about a meter's range of the car, then it sends the message back to the car over 433 megahertz saying, yes, I'm the key fob, I'm in range, unlock the door, and the door will unlock. Now, the relay station attack involves two attackers, each with a box of tricks. And basically the scenario is your two attackers follow the target, let's say to a supermarket car park. One attacker stands by the car while the victim goes and does their shopping. Attacker 2 makes sure that they walk very closely to the victim as they're walking around the supermarket. And attacker 1, who stood by the car, holds the handle of the car. It sends the signal via 125 kilohertz to their blue box. The blue box proxies the RF bandwidth over long-range comms to the red box. And basically the car thinks that the key fob is right next to the car and the door opens. That picture there is of some kit that we use as part of assessments of this type of technology. And we were doing a test only the other day on a brand new vehicle. I won't even tell you what country it came from, but it's a brand new vehicle that's still vulnerable to this. There are many, many vehicles that have remote keyless entry enabled that are vulnerable to this attack, which is why it's the method of choice of organised crime at the moment. And when you hear about high-end vehicles being stolen and shipped abroad, this is the technique that they're using typically. In fact, we even heard the other day, because through one of our partner companies, they deal a lot with police forces who are involved in trying to track down these organised crime gangs. And apparently the latest technique that they're using is when they go and break into a car using this technique, they carry a pocket full of broken glass, and they'll sprinkle the broken glass on the floor next to where the car was, just to hide the fact that they've used a relay station attack to steal the car and make the police officers think that they've smashed the window. So longer range attacks. I talked about telematics. The primary communications mechanism for telematics is the mobile network. Telematics normally communicates either via a TCU component, telematics control unit component within a head unit, or a separate TCU box somewhere in the vehicle. We use these RF shielded boxes during our assessments so for example, that black box there is a usurp software-defined radio. We can spin up a rogue mobile base station using that. and then we can put the telematics box inside the RF shielded box. It will then connect to our base station rather than the public base station. We can try doing things like man-in-the-middle attacks, intercepting the data between the telematics unit and the telematics service provider. We can also fuzz the radio baseband on these telematics units. GPS is a really interesting one. I mean, this is not just for cars. This is, all of transport and also, personal handheld devices. GPS is relied upon so much these days. But within vehicles, some of those scenarios that I talked about where services are leveraging the capabilities of telematics, they rely on GPS. So, for example, if you've got the eCall service, a European service where emergency services are automatically called when your car crashes and the airbags are deployed, that uses the GPS information received by your car to tell emergency services where to send the ambulance to. So, relied upon quite heavily. Now, what kind of things could we do if we could emulate the entire GPS satellite constellation? Well, obviously we could spoof the location, which is a bit obvious and a bit dull, unless it's an autonomous vehicle, in which case it's very dangerous. More interestingly, we can do things like spoofing the date and the time. So we've got a virtual time machine, which enables us to do things like make the GPS receiver think it's this specific date at this specific time. And we can test for the Y2038 bug when the 32-bit address space wraps to 0. So kind of similar to the Y2K bug, really. And we see lots of systems in transport that are relying on very accurate date and time information that we can manipulate. Of course, we can also fuzz the GPS radio stack, and we can do some creative attacks, such as the center of the earth attack, which I'll demonstrate in a minute. So I've got a few videos of these.
So what we have here is an example of spoofing the GPS location. We've got a head unit here connected to a software-defined radio. It's actually a Blade RF. And the Blade RF is emulating the entire GPS satellite constellation. And you can see from the screen that we're actually in central London, not far from Buckingham Palace. In fact, we're in an office in Cheltenham. In this example here, we're in the same office, and the head unit now thinks that our location is in the middle of the Pacific. It's actually Easter Island. In this final example, we're here in the same office location again, and the head unit is now quite confused. It's not quite sure where we are, because if we look at the location, the latitude and longitude are pretty much 0, and the altitude is set to minus 6,371,000 meters, which is actually in the molten core in the center of the Earth.
Last year we did some research looking at DAB radio. As I'm sure you're all aware, in the UK, all new vehicles, or at least the majority of new vehicles, are fitted with DAB radios these days. And it massively increases the attack surface remotely of head units because of the complexity associated with the DAB protocols. So not only is the underlying protocol multiplex data very complex, and you can inject potential vulnerabilities into there that when the receiver parses those, it triggers memory corruption type vulnerabilities. The DAB protocol allows you to layer other protocols and services over the top. So for example, you can send, in addition to a range of different audio codecs, you can send images, so JPEGs and PNGs. So this is typically used for showing like album artwork, and also, you know, if you listen to a radio station, maybe a photo of the DJ that's currently on. You can in fact send video over DAB. I've never seen it actually implemented, and I think it would be pretty low quality, but the protocol stack allows you to do it. It even has support for sending IP and Java. So what could possibly go wrong? So we developed a tool called Dabble that allows us to test all of this, and obviously DAB is a broadcast medium, so if you find a vulnerability that relates to a specific type of vehicle or certain type of head unit, you can send one attack and send it to multiple vehicles simultaneously. So some of the common themes that we've seen, there's definitely inadequate segregation all over the place, not just between different CAN segments. So the stuff that Dave was talking about, you tend to see multi-CAN vehicles these days, whereas in the olden days you'd have like one flat CAN network and all the ECUs connected to that. Now you have multi-CAN networks with high-speed CAN and medium-speed CAN, and then you have gateways in between them. But those gateways aren't necessarily security gateways, they're just mechanisms for routing between them. And when we have seen security gateways, as Dave said, we've found quite a lot of vulnerabilities in CAN gateways. It's interesting because, you know, CAN gateways are essentially a firewall for the CAN network, and if you think what it was like in the network infrastructure world in the late 90s, when, you know, network firewalls were first starting to be used, there was this concept that you throw a firewall in and it solves all your security problems. There's definitely an element of that in the automotive world, and not necessarily an appreciation that the security of that the configuration of that security device is extremely important. It's not just the presence of a security device. Lots of what we call the embedded systems mindset, so security through obscurity, a misunderstanding of you know, what needs to be protected and how it needs to be protected, and that's basically down to the fact that a lot of these ECUs historically haven't been onwardly connected to, you know, the internet or telematic service providers, or, you know, Wi-Fi networks, so they haven't had to think about security in the same way. It's always been a box that you need to get physical access to in order to attack. Infotainment systems, we're starting to see more and more using more conventional operating systems. You know, historically, 5 years or more ago, you would see more esoteric implementations of operating systems on head units. You know, kind of more real-time operating systems. I mean, you still see those today, like QNX, for example, but we're starting to see a lot more Linux on infotainment systems. And there's, again, with this kind of embedded systems mindset, the kind of engineering teams within the automotive space haven't necessarily got the background knowledge and expertise in cybersecurity to understand what hardening processes need to be applied to these operating systems. So again, you know, poor, easily guessable administrative passwords we see all the time. And we see assumptions about security being provided by the mobile networks or the telematics services, because it's such a connected ecosystem, that going back to that big picture I had at the beginning. If you're developing a telematics solution that involves, let's say, a smartphone app that's communicating with a telematics service provider, That telematics service provider is sending its data via a mobile network operator. That's then got to connect to this telematics control unit that's developed by somebody else, that's embedded in a car that's developed by somebody else. There's all kinds of assumptions about who's doing which bits of the security, and sometimes those assumptions completely break down, which is why when we do, for example, man-in-the-middle attacks against the mobile network with a telematics unit, and we can do a downgrade attack from 3G to 2.5G, or to 2G, sorry, so that we can, intercept the data. We, in some instances, find that the developer of the telematics solution has just made the blanket assumption that it was the mobile operator's responsibility to encrypt the data. So it's all in the clear. And now we're man-in-the-middling it, and we can send the data to the telematics control unit to say, unlock this vehicle. And finally, we're seeing integration of functionality in a bid to reduce driver distraction and improve safety that's actually at odds with this segregation requirement to improve cybersecurity. So a good example of this is these ADAS safety functions. So in the past, you'd have had a button on the dashboard that you'd have pressed to say, right, I want to turn on advanced emergency braking. Now, it gets to the point where you've got so many buttons on the dashboard, it's distracting the driver and it's causing a safety problem. So what do? You include that functionality as a tick box in the head unit rather than a physical button. But then if you manage to compromise that head unit via a Wi-Fi attack, you can now just find the function that turns off the advanced emergency braking, whereas before it was physically separated and you had a button, and that communications path went nowhere near the head unit. So that's quite an interesting one, and we're seeing more and more of that. So how does the industry fix this stuff? We're great advocates of Secure Development Lifecycle, so basically considering security right from the beginning, rather than getting to the end, going for we need a pen test of this solution before we go live, and then finding out you've got a fundamental design flaw and you've got to start from scratch again. Okay, 5 minutes left. So yeah, I'm sure a lot of you know about the SDL. I won't talk about it in great detail, but that's it essentially. It's considering security right from cradle to grave of a system. What could be done? Awareness. The industry, the automotive industry, still needs the awareness of what these risks are to be raised. Cybersecurity standards need to be developed. There are a number of standards under development, and there is a it's only because I'm not connected to a network. There's the most mature of those is actually some guidelines from the Society of Automotive Engineers called J3061, and it's about guidelines when developing vehicle systems. There's an ISO standard that's also being developed, but that's a long way off at the moment, from my understanding. So as I said, they need to follow the Secure Development Lifecycle, and of course, independent security assessment is key. So making sure that when they're developing it, they're not marking their own homework. Thank you very much. Any questions? Yep.
Have you seen any PKI being deployed to actually authenticate things?
So we are.
Telematics units, yeah.
Yeah, there's been a lot of talk about trying to implement PKI within the CAN network, so that ECUs authenticating with each other. But we've not seen any of that in real-world implementations yet. I don't know, Dave, do you want to comment on any of that? Because as a result of some of your...
We've not seen it. I know
It's something that we know some of the OEMs, the car manufacturers, are discussing and thinking about whether it's applicable to their vehicle networks. And the important thing to think about here is the fact that the CAN network, this vehicle network that's in most vehicles, is very, very old. And a lot of the OEMs have actually started to appreciate that their next generation vehicle platforms could use a different network that would lend itself more to security mechanisms that aren't really applicable to CAN.
There is actually an ISO standard, I can't remember, I think it's 15764 or something, but that is the use of PKI over the CAN bus for diagnostics. But the problem is at the moment is none of the ECUs have a secure storage mechanism for the cryptographic secrets required to securely implement PKI. So you could have the ECUs, you could use PKI, but where are you going to store your cryptographic secrets unless you've got secure boot?
More in the other direction, so for example, the telematics, you know, that you could then use it so that you know you're actually talking to the right endpoint, so that you're running the little tap. So
We've certainly seen examples of it in telematics rather than the vehicle networks.
So that's implicit in 4G and 3G, isn't it? The mutual off between the base station and the...
yes,
But
you don't trust that. You don't trust the intermediate network, you don't trust the mobile network. You need to secure it from the actual car all the way to the actual telematics server.
Some of the telematics providers are thinking about how they could implement that. Yeah, it's not something that we've seen, you know, real world examples of. So yeah, yep.
Have you only been doing research into cars and domestic vehicles, or have you been looking at commercial vehicles as well? Like, for example, tachographs and lorries.
Yes,
Dave. In fact, we can say one of our reference clients is DAF Trucks in Eindhoven, and Dave's been heavily involved in that, so you can talk a bit about that.
So that's with trucks. It's even easier to do exploitation stuff on CAN because you've got J1939 FMS, the Fleet Management Standard, which standardises all the CAN messages in the truck and what they do. Well, not every single one, but the large subset. So there'll be a message for air braking, there'll be a message for reporting the fuel use, there'll be a message for changing how the diff works and things like that, and they're all standardised. So you could easily look at those and figure out what they are. Yep, sorry.
How do you mitigate the relay station attacks you talked about?
It's a very tricky one. It's why it's still prevalent across, you know, many different vehicles. There are a number of mechanisms that people have tried to use using timing, because especially if you want to proxy it a really long range. I mean, the attack that we've got will work over a kilometre. But if you wanted to use it, you know, between countries via the 3G network, for example, you're introducing delays in there which can be detected, and you can use that as some kind of mitigation.
There's mitigations in military hardware, but you're not going to get that implemented in a car due to the expense.
That's really important point, actually. All of the security features that need to get implemented in cars need to be as cheap as possible, or the car companies just won't adopt them. I mean, the car industry has known about that relay station attack for 8 years. And if the current mitigation that's available for it is too expensive, they won't put it on the cars because they'll lose competitive advantage in what is a very competitive market.
There are manufacturers who aren't vulnerable. You seem to suggest that the ones...
Oh, the ones that aren't vulnerable are the ones who aren't using remote keyless entry.
So yeah, basically they shouldn't be selling it as a feature when they know that it is an issue.
But it's handy. It's handy.
Exactly. You make the risk decision. You Yep.
So what's the situation like with normal key fobs at the moment? And I think there was wasn't there a Volkswagen one recently? There was a tiny amount of entropy in the keys.
Yeah.
So he had
So,
General fairly all right now.
so, I mean, it's down to, again, that's a cost issue. So the technology that they're using in the key fobs, the chipset that they use, there is an alternative chipset that they could have changed to a long time ago that would have meant that attack wasn't possible. But that chipset is more expensive. So, yeah.
The Volkswagen one, isn't that because they didn't solve all the pins down? I thought that was the problem. It was only using so many bits of the entire, that the chipset actually had. It was one physical thing.
But it was down to the capabilities of the chip and the fact that the chips that they were using were there was an alternative chip that they could use that would have mitigated the